I'll start by just acknowledging a few people. The work is really based all on some former students who've come through my group over the years. Jacob Assman, Ting Lin, Christoph Loft, and Regan Chandrabaran. I'll show work from all of them, as well as a number of collaborators who've helped with other parts of the problems that I have less expertise in, or have helped with implementation or other considerations. So they were all really integral to this work. So a few words to kind of set the stage for the problem I want to dig into. The way I kind of think about this ground motion problem is we first start with kind of the earth science as part of the problem. So we've got some location, and I want to think about some site-specific assessment today. So we have a facility located somewhere in the world, and there is potential for earthquakes nearby that could cause shaking and adverse impacts on the structure. So we start on the left-hand side here with a seismic hazard analysis. We need a characterization of nearby seismic sources and the potential sizes and locations of earthquakes that they could produce, described probabilistically. Then we make probabilistic predictions about the ground motions that could result at our site, given each of those potential earthquake ruptures. And we integrate that all up in a probabilistic seismic hazard analysis. And one of the outputs from that analysis is a response spectrum. And this is typically associated with some kind of rare level of ground shaking that we would predict at our site. And then that response spectrum is then utilized heading into our computational dynamics problem. We'll take that response spectrum, we'll find some ground motions that are compatible with that response spectrum, either recordings or simulations. Those are then inputs for numerical modeling of the structural performance. And here I'm thinking about, again, detailed analysis, right? If we're doing all of this hazard analysis, it's probably a relatively involved project. And I'm thinking about the context where that structural performance is assessed with a nonlinear dynamics model. So we've got deterioration mechanisms and kind of some complex relationships between those input ground motions and the response of the structure. Okay? And what I want to dig in today on is this middle piece here, this target response spectrum. So that's really an important link between what the earth scientists are doing to tell us about potential seismic hazards and what we as engineers are doing to infer the structural performance associated with that. And as I'll to foreshadow a little bit, I'll say that the way we specify that response spectrum can have really big impacts on the way that we make inferences about the performance of the structure. And to repeat my opening comment. Okay, so what I want to do then is I kind of have two parts to the presentation. For the first half or so of the presentation, I want to just give a little background or kind of broad explanation about characterizing response spectra. And I'm going to talk about the conditional mean spectrum in particular, and just to give a little bit of explanation about what this concept is as a target response spectrum. And then in the second half of the presentation, I want to talk a bit about what can we do with those insights in terms of specifying response spectra in building codes and other regulations, and how do we kind of formalize this process so that it can be used in structural assessment. I'll talk a little bit about some of my experiences, as well as what the US building codes are doing now in this regard, and a little bit of study we've been doing recently to evaluate if the current code provisions are appropriate in terms of meeting the goals that we have out of this assessment procedure. Okay, so let's get started with that. So traditionally, that middle target response spectrum has been a uniform hazard spectrum, and I'll put a little asterisk there that sometimes we make some modifications. We've got an idealized code shape, like a multilinear shape. And some places we use these risk-targeted spectra that are a little bit of a modified uniform hazard spectrum. But I think conceptually, if we think about a uniform hazard spectrum, that's really pretty close to the basis for a lot of the response spectra that we use in, particularly in kind of the building assessment practice and building code context and things like that. And just to make sure we're all on the same page, this uniform hazard spectrum, what we do is we do that seismic hazard analysis I pointed to on the previous page. And so what I've got here plotted are ground motion hazard curves for an example site. And so we've got three curves here, plotting spectral acceleration and versus the annual rate of exceedance. So over on the left, we've got the low amplitude ground motions that are exceeded frequently with high rates. And then as you move to the right, this is higher and higher amplitudes. And the three curves are three metrics of ground motion intensity, ranging from short periods to longer periods. And so for each spectral acceleration period, we've got a different ground motion hazard curve. And to build a uniform hazard spectrum, we just pick an annual exceedance rate off the vertical axis. We go pull the amplitudes of the spectral accelerations from those different curves. And then on the right-hand side, we just draw those points together. So we've got the spectral acceleration period plotted on the horizontal axis, and then the the spectral acceleration itself plotted on the vertical axis. So I've got it plotted there for 2 return periods. And you can take the 3 points off the left plots, get some points from other periods, and fill it all in, right? And so sometimes we use the spectrum directly, sometimes we draw some lines through it and idealize it, and use that to represent the ground shaking hazard, okay? And so that's been a basis for many of our codes around the world and many of our different evaluation procedures. The challenge here, though, is that response spectrum is not the response spectrum of any one ground motion, right? It's a collection of points from a collection of independent analyses, and we've plotted them all together because it's a very convenient way to summarize a lot of information. You know, each point on those uniform hazard spectra has the same rate of exceedance, so we've got some sort of equivalence from point to point, but it's not the spectrum of any one ground motion, right? It's just an aggregation of a lot of analyses. And so that'll be important here coming up. So let's deconstruct that uniform hazard spectrum a little bit here. I've got a uniform hazard spectrum pulled for a site in Southern California near Los Angeles. So this is a highly seismically active part of the world, and a part of the world where I work a lot. So it's useful for illustrating a few points. So we can pull this uniform hazard spectrum. I took this from the US Geological Survey, which is the US agency that produces this data for most of our engineering work in the US. And let's say that I was interested in a structure that has a period of 1 second. So I'm interested in ground motion amplitudes at about 1 second. And for this particular site, this is a 2% in 50 years probability of exceedance hazard curve, and the amplitude's about 0.9 G. So I might be interested in 0.9 G spectral accelerations at 1 second as a loading condition for my assessment. And we can do a ground motion disaggregation. Some of you might know these things. If not, what it is this is a conditional distribution of the earthquake sources that contributed to that 0.9 G spectral acceleration at 1 second. This is kind of a standard product out of hazard analyses. And so the horizontal axes here are magnitudes and distances of earthquakes, and then the heights of the bars are the percent contribution from those types of earthquakes to this ground motion at this particular site. So you see this big spike kind of off to the left of the figure, and those are magnitude 7 earthquakes about 10 kilometers away from the site. There's a big active source there, about 10 kilometers away, that produces earthquakes every 200 years or so, and so it's contributing a lot to hazard at this site. So magnitude 7, I think to be more precise, it's 12 kilometers away. So let's keep those numbers in mind because I'll use that for an example for the next few slides. So if I take a magnitude 7 earthquake 12 kilometers away, we have these ground motion models that make predictions of ground motion amplitudes. If I just go predict the median amplitude from one of these models, I get this black line here, which is much lower than the uniform hazard spectrum. At that 1 second period, it's only about 0.3 G. So we've got this big gap between what a magnitude 7 earthquake 12 kilometers away produces on average and what this response spectrum is. And what's the extra ingredient here that closes that gap is what we term epsilon. So this is kind of the residual between a particular earthquake's ground motion intensity and its median prediction, right? So the ground motions are highly variable. Some are much bigger than the median, some are much smaller. And in this case, for this uniform hazard spectrum, the conditional epsilon is 2, saying we're expecting a 2 standard deviation larger than median ground motion. And indeed, if I plot a median plus 2 standard deviations prediction from a ground motion model, we're back to around that uniform hazard spectrum. So this is an important concept that in a lot of seismically active parts of the world, when we're designing for rare ground motions, like a 2% probability of exceedance in 50 years, so a 2% probability of exceedance in 50 years ground motion, that's something that occurs once every 2,475 years, 2,500 years. But I mentioned this earthquake source produces magnitude 7 earthquakes every 200 years. So there's this discrepancy between this 2,500 year return period that I'm targeting and the return period of the earthquake means that I'm usually designing for stronger than median ground motions in those conditions. And so this big difference between median amplitudes and these design amplitudes is appropriate because I'm trying to design for this rare condition, and so that's naturally associated with a stronger than average ground motion amplitude. Okay, let's look at some real ground motions. So here I've got the median spectrum in black here, the median plus 2 standard deviation spectrum in dashed black, so the same lines as the previous slide. And then in green are plotted the response spectra of real recorded ground motions that had about a magnitude 7 and were recorded about 12 kilometers from the site. So just collect up observational data, and they're relatively consistent with the predictive model, which is natural because the predictive model is based on observations. So about half the ground motions are above the median spectrum, about half are below. And on occasion, we make ground motions with these response spectra way up 2 standard deviations up, right? So there's, I think, 20 ground motions plotted there. So we would expect about 1 out of 20 to be 2 standard deviations larger than the median, and indeed we see that. And in fact, in blue, I've got 1 ground motion highlighted. So this is the response spectrum of our magic ground motion that we want, right? This was a ground motion from a magnitude 7 earthquake, about 12 kilometers away from the rupture, and it has a 0.9 G amplitude at 1 second, which was that condition that I started with, right? And so it's strong enough at 1 second to be matching this design spectrum. But at other periods, it's not necessarily up at 2 standard deviations, right? So these residuals in the amplitudes are not perfectly correlated from period to period. So if you look out at 2 or 3 seconds in this response spectrum, that blue spectrum is much lower than the 2 standard deviations. And similarly, over at shorter periods, it's much lower, right? And so back to my point that the uniform hazard spectrum, which is kind of like this black dashed line, that's not the spectrum of any one ground motion. And we see from these green motions that some ground motions are up at that high amplitude, but they're not up at that high amplitude at all periods in any one ground motion. And so I want to think about how we could recognize that in our design procedures. So what we do is we can think about these epsilons, these residuals between the median prediction and what we actually observed. And so that's computed. There's a formula here, I won't dwell on it, other than to say it's just difference between observations and median predictions in terms of number of standard deviations. And these amplitudes are log-normally distributed, so we do everything in log space. We just take logarithms, and then it's a nice kind of the response spectrum is like a Gaussian process effectively. So we can do nice statistics on that. But I'll kind of plot things in linear scale just for interpretability. So we can compute these epsilons for this particular ground motion relative to its prediction model. So at the period of 1 second, this ground motion was actually an epsilon of 2.3, not exactly the 2 that I wanted, but close enough for illustration. And you can compute those epsilons at other periods as well, out at a longer period and a shorter period. So this is 1 ground motion. If we do these same epsilon calculations for several hundred ground motions, I'll plot those here. So this scatter plot up on the right is a plot of epsilons at 1 second versus epsilons at 2 seconds. And so our particular ground motion we're looking at is out here at 2.3 for epsilon at 1 second and 1.4 for epsilon at 2 seconds. We've got lots of other points, some of them are positive and some of them are negative. And so you can see the scatter plot there. You can do the same thing for other pairs of periods. So here's 1 second versus 0.2 seconds. So you see kind of nice elliptical plot, scatter plots here. These look very nicely multivariate normal, done statistical tests and things. So we'll just use kind of multivariate normal statistics here. And so that means we get nice formulas like given an epsilon at 1 second of 2, the mean epsilon at 2 seconds is going to just be the correlation between these epsilons, which is 0.75 in this case, times the conditioning epsilon at 1 second. And you can get a conditional standard deviation as well. This is just multivariate normal formulas. Over at 0.2 seconds, the correlation between the 1 second and 0.2 second residuals is smaller. It's only 0.44. So the conditional mean is smaller in that case, and the conditional standard deviation is a bit bigger. All right, so we can repeat that calculation over all pairs of periods, and then we can fill in what we call the conditional mean spectrum. So we're going to take that magnitude 7, 12 kilometer condition that we started with from our hazard analysis. We're also going to take the epsilon at 1 second of 2 that got us to that 0.9 G amplitude that came out of our initial hazard analysis. But then at all the other periods, rather than draw together this uniform hazard spectrum, we'll take the conditional mean values of the epsilons at those periods. So out at 2 seconds, right, we saw that the conditional mean epsilon was 0.75 times the conditioning epsilon, so 1.5, and over at 0.2 seconds, we've got a smaller number. So you can draw those points in over all these other periods, and that's this dashed red line. And we call it the conditional mean spectrum because we've conditioned on that spectral acceleration amplitude at a conditioning period, conditioned on the rupture characteristics that drove that, and we fill in the conditional mean at the other periods. And this is now plausibly observable in a single ground motion because we've carried these statistics through. And just anecdotally, that blue response spectrum is still sitting there, and you can see it kind of tracks next to that conditional mean value, is giving us some sort of ad hoc observation that we see some consistency here. Right? We can also draw conditional standard deviations at these other periods. Right, so we have no uncertainty at the 1 second spectral acceleration because we conditioned on that value. At the other periods, I've got plus or minus 1 standard deviation bounds here drawn, to reflect the uncertainty at these other periods we didn't condition on. And that just comes out of those multivariate normal statistics that I showed earlier. All right, and we can call that a conditional spectrum. It doesn't have a mean value anymore. You can represent a full distribution. Okay, so with these targets, you can go then select ground motions. So we'll do this, build that target spectrum, and then go find ground motions consistent with that target spectrum, either the mean or the full distribution. And that'll represent kind of realistic loading conditions for your site. Here I've got plotted for 4 different return periods at that example site, what those ground motions might look like. And the shape of this spectrum is changing from kind of the lower left. If you look, this is kind of more of a median ground motion at a lower amplitude. As we get to higher and higher amplitudes, the spectrum gets a little bit peaked at that conditioning period because we've gotten to a pretty rare amplitude at that conditioning period, and we don't expect to be equally rare at the other periods, and so we get this somewhat peaked shape. And so the shape of the spectrum varies with amplitude. The shape of the spectrum is also going to vary from location to location, representing differences in the seismic characteristics at the location of interest. So we have this site-specific, amplitude-specific ground motion selection. But if we really want to, we can carry through all these. Actually, let me say one more thing before I get to that thought. So there's a little bit of extra work and a little bit of extra thought to think through this, but it makes a big difference in terms of our assessments. So here's just a taste of what we might see. So this is a steel frame building that we analyzed for another project with some colleagues. And this is a nonlinear dynamic model. We've got these lumped plasticity beam column connections that have all sorts of cyclic and within cycle deterioration, negative stiffness representing kind of buckling in the connections and all of this. And we model these this building using ground motions like the previous slide, all the way out to collapse. So this is a plot over on the right of ground motion amplitudes at 1.5 second spectral accelerations versus probabilities of collapse that we get out of the repeated analyses. We did the whole process once with uniform hazard spectrum ground motions, and that's shown in black, and then once with conditional spectrum ground motions, like from the previous slide, shown in blue. And maybe to give you a little bit of intuition, so that we're effectively using, if I back up the red spectrum or the dashed black spectrum as our 2 spectral targets for the ground motion selection. And because this is a building we're modeling all the way out to collapse, we need to get to kind of high amplitudes at elastic modal periods in order to really get the building excited. But then as it's deteriorating and it's softening and losing stiffness, its effective period is shifting out to much longer periods. And out of these longer periods, there's a big difference in the amplitudes between the uniform hazard spectrum motions, which are not really the spectrum of any one motion, versus the conditional mean spectrum motions, which kind of more realistically represent what we can see in one ground motion. And so because of that difference in amplitude, we see lower probabilities of collapse from the conditional spectrum ground motions, which we think are more accurate. And just to pick a point on this curve and try to bring it home, at a 1G spectral acceleration, the conditional spectrum predicts a 0.2 probability of collapse, and the uniform hazard spectrum ground motions predict a 0.8 probability of collapse. So really a massive difference for, and that's as big of a difference as we ever see from like modeling uncertainty in the buildings. You can really change building characteristics pretty substantially and not see differences this big. So the choice of loading is really important in these types of problems if we're trying to get at collapse reliability. Okay, so this is kind of a full research style, do lots of ground motion selection, step through lots of different amplitudes. That's really not what happens in design practice, right? This is too resource intensive and too many analyses and too many ground motions to select. And so the other piece of this puzzle that we're thinking about is how to codify this and how to use this in a more simplified manner. And what's important there is usually in a code check, we're checking at 1 return period, 1 ground motion amplitude, and checking was our performance satisfactory or not, right? And so you might think about this, maybe coming over to the right figure, if this dashed black line was our uniform hazard spectrum, and we were trying to break it up into this conditional mean spectrum, the choice of the conditioning period is important here, right? So I might condition at an elastic modal period of my structure, but if it softens, the building softens through the analysis, I've got kind of lower intensity that I've loaded it with, but perhaps I want to condition out at the softened period and get the high amplitudes there and have lower amplitudes at shorter periods. So those are all plausible loading conditions. And so the question is how to handle those multiple loading conditions, which I think is equivalent to having multiple conditioning periods. How do we handle that in a checking procedure when we don't know ahead of time what exactly the periods are that are critical for loading the structure, right? We're trying to explore that through the assessment. So one way to think about this conditional spectrum calculation and these conditioning periods, sorry, I fished around my slides a little bit this morning. So let me say, in these checking procedures, this is a pretty popular procedure in some circumstances. So these are all structures that have been assessed using these conditional mean spectrum checks. So nuclear power plants is kind of an interesting case because we have these very massive structures, sometimes with long periods, but they have equipment inside of them with very short periods that are sensitive to high frequency excitations. And so if you build a uniform hazard spectrum loading that hits all of that stuff in a single ground motion, you can really hit the structure pretty hard. Whereas if you separate out into these different conditional mean spectra, you might get a ground motion that loads the high frequency components and one that loads the low frequency components of the structure, but not in the same earthquake. And that has big implications for implied performance. Similarly, for large dams, there's sometimes very low frequency modes and very high frequency modes. This is this lower building. This is a base isolated structure, very big. This is Apple's headquarters. It was built a few years ago. Base isolated, so it's got isolators with a period of like 4 seconds, but then there's superstructure features with much shorter periods, and this was analyzed with conditional mean spectra to kind of separate those. And then high-rise buildings is really a popular case. So most of the high-rise buildings built in the western United States now use this conditional mean spectrum procedure because you get kind of very low frequency modes for kind of the first mode of the building, but then you have other types of response features that are sensitive to higher frequency excitation. And so I'll think about the building, the high-rise building case in particular, because that's a really common situation in the western US and other parts of the world. I know it's used as well. And so this idea of these conditioning periods, I think about one way to think about it is to think about a reliability analysis with a design point, right? And so the full-blown kind of select ground motions at multiple intensities and step through these fragility functions, I think about as kind of sampling ground motions across an entire probability distribution of spectral accelerations at different periods. I'll plot in just 2 dimensions here, but it's a higher dimensional problem. And our structure is some sort of function of these spectral accelerations, plus a function of other characteristics that are not defined by spectral acceleration. So let's call that delta here in a limit state function. Okay? And if we could step through this entire probability distribution with ground motions and check for failures and non-failures, we could find kind of probability of failure of the system and decide if that's acceptable. But in a checking procedure, we don't have the luxury of kind of stepping through everywhere. So what we do is we just check at a kind of more simplified sets of loading conditions. And one way to think about this is if this limit state function was really dominantly a function of one spectral acceleration period, then our limit state function would be kind of vertical as a function of that one spectral acceleration period. Our design point would be the spectral acceleration with some probability of exceedance associated with our reliability goal. And then there's an adjustment to deal with this delta. So the spectral acceleration of 1 second would be, you could derive it through some reliability calculations. The spectral acceleration of 2 seconds is, because it's not in the limit state function, the design point's gonna be at the conditional mean value of 2 second spectral accelerations given this timeline. So that naturally falls out into a conditional mean spectrum at this 1 second condition. We don't know if that's actually the limit state function for our structure. Maybe our structure is a function of spectral acceleration of 2 seconds. And so we'd get a target 2 second spectral acceleration plus a conditional mean value at 1 second, and similarly for the other dimensions not plotted here. And so you could think about these conditional mean spectra at different conditioning periods as design points. And then what we can do is we can do our check of our structure at those design points. And if we have adequate performance at those design points, we can infer that the limit state function is somewhere further out to the right and above. And we can infer that we've got acceptably low probabilities of failure. So those would be natural points to check at. The uniform hazard spectrum is kind of represented by this black point, where we take marginal distributions of our individual spectral accelerations. We find some point out of those probability distributions, and then we just connect them together. But that's not necessarily an optimal place to be checking, especially in higher dimensions. You can kind of really put that point out pretty far away from your probability distribution. So for those of you reliability oriented, that might be a concept that resonates here. We did some derivations to try to draw that connection a few years ago. Okay, so now to building codes, the kind of second part of the talk. So thinking about those high-rise buildings in particular, so we have a set of codes and standards that governs those designs. In the US, ASCE 7 is the standard that specifies seismic loading conditions that's used in most of the design of new buildings. And since 2016, it's allowed 2 different options for your ground motion selection. So you still do hazard analysis as usual. You can choose to use a uniform hazard spectrum, or uniform hazard spectrum with an asterisk for some other modifiers that are not important for today. And so that's the traditional approach that's been in the standards for decades. But now you can also use conditional mean spectrum. And the way that it was codified, and the goal is to allow this procedure to be used, but allow it to be relatively robust so it's not kind of misused. And some of the key concepts that are in there is that you have to use 2 or more conditional spectra. So that's representing these different loading conditions that might be important for your structure. And there's some period range of this response spectra that you're responsible for considering. And within that period range, the envelope of these conditional mean spectra have to be within 75% of the UHS, right? So the worry here is that, like in this situation, if I had a conditional period of 0.5 seconds and a conditional period of 2 seconds, at 1 second here, those 2 spectra, either one of them is very high in amplitude compared to this uniform hazard spectrum. But I know I could get a high amplitude ground motion at 1 second, and I don't want to have a gap there, but I never loaded the structure to see if that would be problematic. So the rule is that at kind of all periods, you have to be within 75% of the uniform hazard spectrum. And so if you have one of these gaps, you have to either fatten out your conditional mean spectra to just make them a little more intense, or you have to add some more conditional mean spectra in those gaps to make sure there's no periods where you're not putting in a high amplitude load. In practice, almost everybody fattens out the conditional mean spectra, so you add in a little bit of conservatism, but you don't do more work. The trick is if you're doing, for each response spectrum, you have to do a separate set of ground motion selection, a separate set of structural analyses, and you have to pass the check, all the design checks in terms of drifts and forces and all these things for each CMS. So each time you add a new target spectrum, you're adding more work. So this option 2 is twice as much work in terms of analysis, but adding a 3rd spectrum is really pretty unappealing to most people. They'd rather kind of split the difference and do two sets of analyses and have a little bit more conservative. And so that was kind of built out of some experience and some judgment, but we've more recently been trying to test this out a little bit more systematically to make sure that we're not missing anything with this type of procedure. So I want to talk to you a little bit about that. So what we were doing is trying to assess that code procedure and just check, is there any way we could break it or get kind of unsatisfactory designs that happen to pass these checks, which is our big concern. Right? So the way we did this assessment is we did kind of building these ground motion targets, did ground motion selection, and we've got 3 alternatives here. I'm going to talk about based on the uniform hazard spectrum, so a conditional, a traditional way of doing this, as well as 2 conditional mean spectrum methods. For each set of ground motion selection, we're going to then do dynamic analysis. And here we were using a 42-story reinforced concrete core wall. So this is a pretty popular type of building in the Western US right now for condominiums and things like that. That white building that I showed in the photo of is this type of structural system. It's about 40 stories tall. And we've got a nonlinear open seas model that's got kind of the key failure mechanisms that we're worried about in there. And we're looking at maximum considered earthquake ground motions, so 24, 75-year return periods, so pretty high amplitude ground motions to do these checks at. So with each set of ground motions, we're going to do some checks, see how the building does, and then we're going to look at building demands. So, and what we did here is we looked at story drift ratios, so the maximum throughout the building height, story shears, and floor accelerations. And the idea was to pick a few different response parameters that are sensitive to different types of loading. So the story drift ratios are pretty first mode dominant in these buildings. And so the kind of long period loading is important for driving story drift ratios, whereas like the floor accelerations are much more sensitive to high frequency excitation. And so we could potentially miss one or the other of those parameters if we don't kind of consider careful conditioning. Anecdotally, I'll say as well, if it's of interest for some of you, the story shears, that's a pretty important design parameter because that influences how much concrete and steel is in the base of these core walls. And when people use this conditional mean spectrum assessment approach instead of the traditional uniform hazard spectrum assessment approach, rule of thumb is you might reduce story shears by about 10%. And so that's a pretty big deal for new design. And it's, for many analysts, it's worth the effort to do a careful analysis if you can justify reducing the design story shears, just as one metric. Okay. So we looked at all those. In each case, we've got a suite of ground motions that we're running. And so we've got a suite of responses. These gray lines in the lower right are indicating kind of individual response results. And the building code is having us look at the mean of those suite of responses. So we're just going to take the mean out as a summary metric here. That's the number we would be checking against acceptance criteria in the building design. Okay, so I mentioned there's 2 conditional mean spectrum selection methods. So let me tell you about those. One of them is, we'll call it CMS ASCE. So this is compliant with that ASCE 7 standard I mentioned. So we'll do 2 target spectra. and we're going to broaden those spectra out until they hit this 75% threshold that's required. So there's a little picture over here on the right. The uniform hazard spectrum is shown in black. In this case, we've got 2 conditioning periods. You can kind of see them as the peaks of these spectra where they touch the uniform hazard spectrum. The dashed line is the 75% threshold we have to hit, and the spectra wouldn't naturally hit that, but we broadened them out a little bit to make sure we got above that, everywhere. We just touched it in a couple places. The other thing I'll note, because it'll be important in a minute, is these dashed vertical lines. This is the period range that the code makes us consider, and whether we do it uniform hazard spectrum or conditional mean spectrum, we've got to look at some period range, and this is double the first mode period to consider nonlinear softening, and down to higher modes periods on the left-hand side to consider higher mode responses. So for this 40-story building, we've got to go from a half second out to about 10 seconds. Sorry, I'm touching the computer. So that's a set of 2 spectra and 2 ground motion suites that would comply with ASCE 7. Then we called the second approach the kind of a theoretical approach. So in this case, we actually took 17 conditional periods, and we said, well, we don't know ahead of time which conditional period is going to be important. So let's just do them all. We'll do 17 sets of ground motion selection, and among those 17 sets of responses, we'll take the biggest one as the response that we're going to check against our acceptance criteria. So the design engineers thought we were crazy for doing this, but we had time as researchers to run these things. And so we ran kind of a whole bunch just to try to get a benchmark of what would happen if we hadn't simplified things down. You'll notice with these spectra, some of them dipped very low at periods away from their conditioning period, but we're not worried about that because we have other conditional spectra that hit the high loading amplitudes of those periods. Okay. And in either case, either the 2 spectra or the 17 spectra, we're going to take the maximum of the mean response we got out of any of those analyses targets as our Okay. So let's check this out. So the first set of analyses we did, this is pretty close to what building designers would do in the Western US. We're going to use our conditioning periods. We're going to choose them based on the building's modal properties. So this 42-story building I told you about, the first mode period is 4.2 seconds. Second mode period is 1 second, and the third mode period is a half second. So that's down at kind of the lower end of the period range you have to think about. So typical practice is to set one conditioning period slightly lengthened from the first mode period, like 20% longer. So these core wall buildings, they tend to soften slightly, even if they're code compliant at these very large ground shaking amplitudes. So we'll go out to 5 seconds there. And then the second conditioning period will typically take it to second mode period. And if there's 3D modes, they tend to group in still kind of two discrete ranges. And so same thing happens for a 3D analysis, even though this is just a 2D analysis here today. Okay? So that's kind of a typical conditioning period selection in practice. And so here's a table of results. We've got the story drifts, the base shears, and the roof accelerations labeled down our rows. With the uniform hazard spectrum, we get a 2.6% drift. Right? This is very strong shaking, so a pretty decent amount of drift out of the building. The base shear is about 20% of the weight of the building, and the acceleration at the roof, which was where always the peak accelerations were showing up at, was 1.3 G. And the CMS theoretical, so if we did 17 sets of analyses and took the biggest of these demand parameters, we get the following, and they're just plotted as percentages, so you don't have to kind of compare units to units. So the story drifts are only 74% of the uniform hazard spectrum story drifts, right? Because we're not hitting all the modes simultaneously with that uniform hazard spectrum, it's reduced. The base shears are reduced a little more than 10%, kind of compared to that 10% number I told you about earlier. And the roof accelerations are reduced less, 90% of the uniform hazard spectrum. The ASCE 7 procedure, that was only the 2 spectra that were slightly broadened. Same thing, we took the max of the 2, and we were pretty spot on with the story drifts and base shears. The roof accelerations we underestimated slightly. Interestingly, we kind of struggled with that one for a bit. At first glance, I was like, oh shoot, we've got a problem. But what's going on is the ASCE 7 only makes us consider down to 0.5 seconds with our conditioning periods. And so you see all of our spectra are quite a bit lower than the uniform hazard spectrum at very short periods, which is actually what's driving these peak floor accelerations. So it's not really a conditional mean spectrum issue, it's really an issue about this period range that we have to consider. That said, floor accelerations is not typically a critical design parameter in these buildings at least, so we noted it and it moved on. It's not really fundamental to conditional mean spectrum as much as this broader issue of period range. Okay. Then what we did is we said, well, that's so good practice with the CMS seems to be working pretty well. What if somebody was bad, right? And what if somebody was not doing a very good job with this, which we have to worry about in a code procedure. Although these tall buildings are typically peer reviewed, you don't want to rely on the peer reviewers to kind of catch everything. So we said, what if we, instead of this 1 second and 5 second conditioning periods, what if we took a conditioning period of 3 seconds and 8 seconds? So not very good because it's kind of separated from the modal periods of the structure. Or what if we went as crazy as we could and we said 0.15 seconds, so way out in like short periods, and like the longest period we could get to is 9 seconds. So I characterize that as a terrible choice of conditioning periods because you're loading like very far away from where the dynamics of the structure are. But nonetheless, it might be code compliant, and so what happens in that case? The spectra themselves are plotted over on the right. So we expand out the table here a little bit with some more ASCE7 rows. And this not very good procedure, we're a little bit low in terms of the base shear. The roof acceleration is kind of compatible. I'm comparing the kind of the 2 rows of CMS in the middle. And then interestingly, this very bad choice, we end up getting a little bit bigger story drifts than the other cases, but the base shears and roof accelerations are okay. And what's helping us here is that 75% floor. So this really bad case, even though we conditioned out at 9 seconds, I got my cursor there showing, we have to keep the amplitudes pretty high from like 2 to 5 seconds where we're actually exciting a kind of elastic response. And so it turns out we've got enough amplitude here to excite an elastic response. And then when the building is softening and being nonlinear, we're still exciting it pretty good. So we got a decent drift out of it. And the other response parameters are pretty equivalent. So I think this floor of 75% is a pretty reasonable way to ensure that we're not going to kind of miss some key loading condition in terms of the frequencies of excitation. And so we ended up kind of walking out of this, at least for this structure, saying the procedure seems reasonably robust and kind of ongoing testing for some other classes of structures. Okay, so to start wrapping up, I want to leave you with a few messages. So first of all, this conditional mean spectrum. I hope I gave you a reasonable overview if you hadn't seen that before of an interesting concept for how to characterize these ground motions. In the US, where I've worked mostly, but in Turkey and Switzerland and some other places I've seen internationally, this procedure's gained quite a bit of popularity. The analysts who've got a very complex system, and they're willing to put in some time doing analysis, but they've got very expensive choices if they've got an over-designed condition, or maybe an analyst who's checking an existing structure that's kind of on the border between being acceptable or not, according to some standard, doing a little bit of extra analysis work to separate out and not have a single ground motion with high amplitudes at all periods. It's really been appealing in some of those cases. I should note, in kind of Western US practice, dynamic analysis of buildings is probably less than 1% of buildings. This conditional mean spectrum is less than all of those 1%, so this is still very much a niche topic. But in those particular cases, for some pretty high importance buildings sometimes, it's gotten to be a pretty popular procedure. And I hope you got some insights today out of why that is and what the concept is. Since, I mentioned since 2016, this has been a part of the US building codes. And there are some simplified rules in there to ensure the robustness, but not create an excessive amount of work. And so hopefully that's interesting for some of you thinking about code provisions or assessment procedures. We didn't have a full set of data to make the initial code recommendations based on, but in the years since we've come back in and I showed you a little bit of how we're thinking about doing that checking. For that representative case study, that's probably the most common building type, these kind of 40-story or so tall buildings. It seems to be working pretty well based on that data that I showed you, and I think we have kind of qualitative reasons to expect that it should work reasonably well. But we also kind of try to lay out that procedure pretty carefully so that we can have follow-on studies with other cases and try to build further confidence. Okay. Finally, I'll note, point you to a website, and there's a QR code to the same website. And I've got citations to the kind of the papers I drew most heavily from today. So if you're interested in digging in a little bit more on the theory here, we've got more documentation there. We'd love to have you head over and take a look at it. There's also some software tools to help with these conditional mean spectrum calculations and even some ground motion selection algorithms to try to ease your workload. So these aren't things you have to implement from scratch. Most everything is done for you. At that point, I'll close.
This was designed for the conditional mean.
Yeah.
The lack of robustness.
Dramatic ending.
Ground motion selection.
Okay, maybe we have a short time.